Hello, today we will be discussing chemical equations and reaction equations, which are balanced using various methods and techniques to ensure accuracy and conservation of mass. In our prior lessons, we obtained knowledge on how to set coefficients and utilize the method of least common multiple for our calculations. We'll also remind you of this method today. Besides that, I'd like to show you another way of equalizing today, which is connected with the concept of an odd coefficient and, accordingly, transitioning into an even coefficient. This is a technique used for balancing certain chemical reactions that proves effective in some cases. Furthermore, I have to say, balancing chemical reactions is a rather challenging and complex task, Of course, there are relatively straightforward interactions where it may not be so difficult to find the coefficients. But there are also interactions where, if you don't adhere to a certain equalization tactic, it may not work out and the equation will remain unbalanced. So now let's remind ourselves how we deal with these equations, and let's remind ourselves of the first method. He is commonly referred to as coefficient selection through the lesser common multiple calculation. Okay, let's go over the following interaction. Let's assume that we have aluminum undergoing a reaction with oxygen. There can potentially be a reaction between these substances. She is responsible for the formation of a substance known as aluminum oxide, which has a chemical formula of aluminum 2O3. At this moment, the equation is still unbalanced because the number of atoms of each element on the left and right sides is not equal or identical. Well, let's remind ourselves of how we work using this method. We determine which element has the highest index value in the given set. As we can see, oxygen has the highest index. Let's underline this element both on the left and on the right. By doing this, we're showing that this element will be aligned first. Its priority is the highest. So between the numbers 2 and 3, that is between the oxygen indexes, we find the common multiple. This is a multiple of 6. Then we start dividing sequentially by the least common multiple. We divide 6 by 2. The division result is placed in front of the oxygen formula, in front of O2. We divide 6 by 3 and obtain 2. The value of 2 is then placed at the beginning of the formula for aluminum oxide. Next, we proceed to aluminum. On the left side 1, that is the first element. When the index is unspecified, it implies a value of 1. On the right side, by multiplying the coefficient with the index, we obtain a result of 4. So for aluminum, the common multiple is 4. We divide 4 by 1 and get a coefficient of 4 in front of the aluminum formula. We divide 4 by 2 and the quotient of 2 is saved. Consequently, our equation turns out to be exactly like this. And I will remind you that substances situated on the left side of the equation are referred to as reagents. The substances on the right are referred to as reaction products. Therefore, the left side is known as the left side of the reaction equation, while the right side is known as the right side of the reaction equation. And between substances, if there are several participants on the left and right, only a plus sign is used. No other signs are displayed. Therefore, this reaction, in addition to that, let's observe, is a compound reaction, as one complex substance was obtained from two simple substances in this instance. However, there can be other varieties of reactions. Let us provide an instance of the subsequent interaction. For instance, there exists this substance known as gold oxide aurum 2O3. This oxide, at a certain temperature when heated, will decompose into gold and oxygen. In this case, oxygen is a gas. This reaction, if you observe it, is similar to the previous one, but like in an upside-down state. So, this is a decomposition reaction. Well, here we go again. Let's start with oxygen. On the left side, he has 3. On the right, 2. Oxygen multiple is 6. Divide 6 by 3. Put a 2 in front of the formula for gold oxide on the left side and divide 6 by 2. Put a 3 in front of the oxygen. Please note that this trio cannot be placed in this location, as some people mistakenly believe that if we insert a coefficient before the entire formula, it implies that we should also place it on the right side. No, that is not how it is done. Now we have 4 gold on the left side and 1 on the right side. As it turned out, gold is divisible by 4. When you divide 4 by 2, the result is a deuce. The F did not get expelled. We divide 4 by 1 and we obtain the result of 4. Alright, our equation is equated and solved. We can verify it in this manner. Therefore, the quantity of gold on the left side is 4, while on the right side there are 4 oxygens, and on the right side there are 6. This is classified as a decomposition reaction. We will illustrate this using the interaction between aluminum metal and iron scale as a case study. This is a compound, specifically a mixed oxide FeO3O4, which is present here. This mixture is commonly referred to as thermite. It is used in welding, for example, in the case of connecting railway tracks together to form a continuous track. This reaction is a reaction that takes place at a specific temperature. Consequently, aluminum displaces iron, leading to the transformation of iron into aluminum, and the transformation of aluminum into an oxide. This chemical reaction is referred to as substitution or a simple substitution process. Alright, let's start with selecting the coefficients. Once again, we choose which of the elements has the biggest impact. This is oxygen. On the left side he has 4, on the right side he has 3. So the overall multiplicity for oxygen is 12. We divide 12 by 4 and we get 3. Let's put this coefficient in front of Fe3O4. We divide 12 by 3, 4 prior to Al2O3. Let us equalize the oxygen content for better balance. Now we can proceed in any order. For instance, let's consider iron. We have a total of 9 units of iron on the left side and on the right side 1. So the multiple for iron is 9. We divide 9 by 3 to get the final answer. 3. Our coefficient remains unchanged. We divide 9 by 1, therefore the result is 9. We're putting on a show in front of the iron. Now all that's left is aluminum. On the left side there's 1 aluminum, but on the right side there's 8 aluminum. So the multiple for aluminum is 8. If you divide 8 by 1, you will get 8 in front of aluminum as the result. When dividing 8 by 2, the remainder is 4. Additionally, I would like to remind you that the reaction equation can also be interpreted as a chemical language when it is heard. 8Al plus 3 Fe3O4 equals sine 9 Fe plus 4 Al2O3, 4 equals sine 9 Fe plus 4 Al2. The next example, where we will equalize using the least common multiple. So let us examine the interaction that takes place between P2O3 and, for instance, hydrochloric acid as a specific illustration or example. This reaction will be an exchange reaction or a double replacement reaction. Therefore, this reaction is going down in terms of exchange. And in order to guide ourselves in the correct direction towards the right side, let's position a small helper frame to assist us. We are merging iron with chlorine. As a result, it ultimately transforms into peronchlorine 3. And secondly, in case there is hydrogen and oxygen remaining in the frame, it is always water. So this reaction will be irreversible. Now let's balance the equation. By the way, for exchange reactions, I highly recommend working according to the scheme. First, we'll level the element in front of the frame. This is the genuine article, so let's begin with it. On the left side he has a pair, on the right side he has a single one. 2 is more beneficial than 1 for iron. When 2 is divided by 2, the quotient is 1. The unit is not written. When 2 is divided by 1, the result of 2 is put in front of FH3 as the numerator. Let's move on. Next, we'll balance the chlorine element, which is outside the frame on the right. So on the left side it's 1, and on the right side it became 6. Write down the deets here. Divide 6 by 1, you will get 6. We are setting the odds at 6. Will you pass the chlorine? Now we divide 6 by 3, the 2 is still present. Next in line, I recommend you align the hydrogen atom. So given that chlorine was ranked second for us, it follows that hydrogen would be the third element in line on our list of priorities. So there are a total of 6 hydrogens on the left side and 2 hydrogens on the right side. So the total hydrogen is a multiple of 6. 6 divided by 1, 6 remains. 6 divided by 2, 3 put in front of the water formula. Now we just need to check the oxygen. He's our fourth in line. Alright, let's emphasize it in a wavy line. And then there are 3 oxygens on the left side, and as we can see, there are also 3 on the right side. A multiple for oxygen would be 3. However, we have 3 oxygen on both the left and right sides. So the equation is equated. So the equation can be read as F2O3 plus 6 HCl equals 2 FCl3 and 3 H2O. So this method of equalization that we just used is called the trial and error method, through the least common multiple. And please note, we are proceeding from left to right in this particular scenario, as that is the established method for balancing chemical reactions. Well, now what the heck is this even-odd method? What type of method is this for equalizing, and in what scenario will this method work? Allow me to provide you with the following example. Okay, let's consider the interaction between sulfur oxide and oxygen. This reaction is super important because it's used as the second step in making some really crucial sulfuric acid. This phenomenon takes place due to the formation of sulfur oxide 6, also known as SO3. So pay attention. In this instance, the principle of initial coefficient selection is not identical to that of this situation. And in this instance, we are discussing the utilization of a unique technique of balancing both even and odd numbers. Okay, let's take a closer look. We'll start with oxygen. However, in this particular scenario, the total amount of oxygen we have is made up of 4 atoms, which is an important detail to consider. And on the right side, upon observation, we can see its number. This element oxygen is composed of a total of 3 atoms. Now let's have a look. On the left-hand side, this number is an even number. And on the right side, kindly hold on for a moment, will you please? And on the right side, this number is an odd number in this particular case scenario. And then you see how this method operates. Since the number on the right is odd and the one on the left is even, we state that an odd number should be transformed into an even number. In what way? Then you must place the coefficient 2 before the formula SO3. Just for your information, it is typically a 2 and nothing else. Not 4, not 6, but exactly 2. Now look, we have a total of 6 oxygen, which is an even number, but on the left it's still 4. Now let's proceed and observe, because for us it is still an assumption how to distribute it in a way that there are 6 oxygen atoms on the left side and it is balanced out with the right side. Let's examine the amount of sulfur we have. And now for S, the LCM reception starts to work. On the left he's alone, and on the right there are 2. And then we divide 2 by 1, place the 2 in front of the 2. Now let's go back to talking about oxygen. Okay, we're facing a problem. The number of atoms on the left and right side is 2 each, but what about the oxygen atom? There are 6 of him here and 6 on the right. That's reversible reaction. Now listen up. Here's what we did first. As the initial step of equalizing, we used a method where we turned an odd number into an even one. Let's provide another example of the identical type. There is a reaction, an interaction occurring between nitrogen dioxide and oxygen. This reaction happens when during a thunderstorm, nitrogen oxide, NO, is formed from nitrogen and oxygen, and then under the action of oxygen present in the air, NO2 is formed. And then, originating from nitrogen dioxide, under the influence of water and oxygen, unfortunately, nitric acid is formed. And that's the reason for the formation of acid rain. But nevertheless, this reaction happens in nature, and it's important to definitely know about it. So, well, now let's take a look. Let's initiate the discussion with oxygen. However, on the left side, we have a total of 3 oxygen atoms, whereas on the right side, we have a total of 2 oxygen atoms present. Here we have odd, here we have even. And here we go again. Before that, we set an even coefficient of 2. Now let's get back to work. All right, we got 2 nitrogens on the left side and 1 on the right. So the multiple for nitrogen is 2. When dividing 2 by 1, the remainder is 2. To divide 2 by 1, you need to place the number 2 in front of no 2. And now we just got to check the oxygen. There are 4 oxygen atoms on the left side and 4 on the right side. This reaction is additionally a backflip. Now let's demonstrate another instance of interaction. When discussing the decomposition reaction of carbon dioxide, it has the potential to occur with the formation of the gas CO and oxygen as byproducts of the process. This reaction is reversible. Let's review how the method works. On the left, we have 2 oxygens, and on the right, the total oxygen is also 3. Both sides of the reaction show the same amount of oxygen. So it turns out that on our left it's even, on the right it's odd. And where is it odd? At this location. Therefore, prior to the CO formula, we established the coefficient as 2. Now there are an even number of gas stations on the right side. Alright, now let's take a look. So we have 1 carbon on the left and 2 on the right in this case. The multiple for carbon is 2, so we divide 2 by 1 and get 2. And 2 divided by 1, the 2 is preserved. And let's check for oxygen. There are 4 oxygen atoms on the left and 4 on the right. That is reversible. And you know, it turns out in the examples that I just showed, it happens that they start equalizing, for example, from one of the methods, let us say from the odd make it even method. And then it proceeds to equalizing by determining the greatest common multiple for the element that has the highest index position within the given sequence of elements. However, it transpires that each equation must still be equated in a certain manner and simplified to the smallest possible whole numbers, as it is not customary to include duplicated coefficients or fractional coefficients in our chemical equations. So, I hope it's clear how both methods work, but once we get some practice in, we'll figure out what we're going to do in the next lessons. But I hope you've got the hang of the equalization methods. Goodbye.